Ladies and gentlemen, we've heard from military experts. We've also heard from our international partners. And now it is my pleasure to introduce our next keynote speaker, who has an academic background, Dr. David Brumley. I'm going to introduce you. He's excited to get up here. Dr. Brumley is the Bosch Security and Privacy Professor at Carnegie Mellon University, the Director of SciLab at CMU Security and Privacy Institute, a professor in electrical and computer engineering with an appointment in computer science, and a founding member of the academic advisor for a world-ranked competitive hacking company. His research interests include all areas of security, with a specialization in software security. Dr. Brumley received his PhD in computer science from Carnegie Mellon University, a MS in computer science from Stanford University, and a BA in mathematics from the University of Northern Colorado. His honors include a United States Presidential Early Career Award for Scientists and Engineers from President Obama, a 2013 Sloan Foundation Award, and numerous Best Paper Awards. Dr. Brumley's security startup, For All Secure, won the DARPA Cyber Challenge that tested fully autonomous full-spectrum attack and cyber defense reasoning systems. Ladies and gentlemen, please welcome Dr. David Brumley.
Thanks. Cool. I'm excited to be here today. So did you know that the Department of Homeland Security says something like 80% of all intrusions are due to a software vulnerability? Now, software vulnerabilities are so highly prized because they give you access to every system that's running that piece of software. So I was really honored in this introduction to go through all these accolades, but really what I identify as is a hacker. I love finding software vulnerabilities, and I love exploiting systems. And the way that we go about finding these software vulnerabilities so we can go break into systems is really simple. You go and you hire a hacker. So this, my friends, is probably the world's best web browser hacker. To give you an idea what this person can do, his name is Loki, at least on the internet, that's what we call him. Over the course of a weekend, he found zero-day vulnerabilities, so brand new vulnerabilities no one else had found, in Google Chrome, Internet Explorer, and Apple Safari. This guy could own 80% of all web browsers running today. Now, he's one of the good guys. He turned over that information to each one of the companies. They were able to patch those vulnerabilities and roll out updates. Some of those updates reached most users within 30 days. Now, no doubt, the DoD has people just as good as Loki. And in particular, in the Army has put a lot of effort into building the next generation cyber soldier. And from what I've witnessed, they're just as good as Loki. But at the end of the day, this idea of we're going to go look for new vulnerabilities, we're going to find these ways into systems, and we're going to have it human-powered, just simply doesn't scale. There's no reason, if we put in the most effective training to identify and train up the world's best, that other countries can't do the same. We don't want to be in a person-on-person battle because you know what? It just doesn't scale. The US has 6% of the world's population. Other countries or other coalitions of countries are going to have more people. And by definition, what that means is they're going to have more people like Loki. We have to do something better. We have to do something different. And to me, when I look back through history, one of the things the US has always excelled at is having superior technology in addition to the superior soldier. We need to look forward and see what that superior technology is that's going to give us that asymmetric advantage. When today, a lot of the way we break into new systems is human-powered. We've been working on this problem. In particular, the way we phrase it is, what if we could automatically check software for exploitable bugs? What if we could do what Loki does, and we could teach a computer to do it? And I'm not talking about just any potential problem in software. I don't care if the font's wrong or the user interface is confusing. What I care about are those bugs that allow an attacker to break into a system. To give you an idea of what this may look like, I'm going to show you a video. And it's a little bit technical, but I think it gets across the right idea. This is a program called iwconfig, and it was used in Linux servers to configure a wireless card to the access point. We all use wireless, so we all know about hitting an access point. And it had a typical software vulnerability in it that would allow an attacker to break into a system. Now, this program wasn't big. It was only 1,400 lines long. It doesn't take a big program to have a problem. What we've built is technology that can take the off-the-shelf binary, the executable you actually run, systematically look through that program and do what Loki does. We find those exploitable bugs. And what I mean by an exploit is the noun. You know, exploit is a verb and a noun. It's something you can do to someone. I can exploit a graduate student. It's also a noun. It's an input to a program. So here, if you start off as an unprivileged user and you just take the output for the tool and run it to iwconfig, you get super user access. So to recap what you saw, is we took executable software, something that you're running on your system, something delivered to you by the vendor, and we were able to autonomously check it for vulnerabilities and produce working exploits demonstrating it was flawed. This isn't the world that we live in today. The world today, we have far too many Lokis that are required to secure our systems. But I think it's the world that we want to be in, where we can simply leverage superior compute power to better secure our systems. We've been on this mission for a long time. It's been a long research road. It's not something that popped up overnight. We've been doing it since 2003. And one of the big breakthroughs that we had is we were finally able to check every Linux program. We spent 3 years of CPU time, and we did it in 1 month on Amazon Cloud. As part of this analysis, we generate regression tests, so when you patch a program, we can check the quality of that patch to make sure it doesn't break your system. Of those test cases, 209 million, we found 2.6 million ways to crash those programs. Think of it, 2.6 million effects, due to, as far as we could tell, 13,875 unique bugs. A single bug can be triggered many different ways. Now, this research raised a whole new problem. How do you report 13,000 new bugs? Something I don't know the answer to today. We've tried, but it's been hard. Out of those 13,000, though, we know 250 will allow a person control flow hijack, meaning that an attacker can run arbitrary programs on your computer. We can also, because we can do this automatically, start talking about ROI. For example, I can tell you it costs 28 cents per bug and $21 per exploit. One of the things I didn't tell you about Loki is when he was able to break into Google Chrome, Internet Explorer, and Apple Safari, he turned over those exploits to the companies, and they also rewarded him with about $250,000. Compare that to the cost of finding vulnerabilities from a machine. So DARPA has been looking at this sort of research. We're not alone. Other academic researchers have been investigating it, and they challenge the community to do essentially the self-driving car of computer security. They called it the DARPA Cyber Grand Challenge. And the Cyber Grand Challenge was to automatically check and protect off-the-shelf software. Now, researchers like me had always been looking at how do we hack into systems automatically. DARPA took a step back and said that's not enough. You have to be able to show that you can autonomously fix them as well. And the way they set this up, I think, is really important to go into because it gets at the heart of cybersecurity as I see it. Cybersecurity is a battle, but it's not something where you're either secure or insecure. It's a battlefield where the attacker gets to co-evolve with you. And so the way that DARPA set this up is they came up with software that they would send all the competitors. I'm showing 3 here. They'd send it to the competitors to try to find vulnerabilities, and those competitors would send back working exploits to DARPA along with proposed patches to fix those vulnerabilities. And it did it completely autonomously. And what DARPA then did is perform consensus evaluation. What that means is my exploits only counted if I could break into other people's systems with them, even after defenses. They didn't stop there, though. They said it's not all about computer security. It's also about performance and functionality. It turned out, according to the DARPA scoring, that if we returned a patch binary that had more than a 5% performance loss, we would probably be better off with the insecure system. So DARPA would do this evaluation, but the next step is really about the evolution. They would send our patches to our competitors. Our competitors would then have a chance to analyze what we did, learn from that, find new exploits, be able to bypass our defenses and send them back to DARPA. They called this a round. The Cyber Grand Challenge went over 95 different rounds, where in every round we had to attack, we had to defend, and the adversary got to learn from what we did. And I think this is super important to get across. Cybersecurity is not a binary value. It's not 0 or 1. It's about how you evolve, how you strategize, how you lay out your plan, and how you cope with an adversary who's learning from you as you do it. So Mayhem was the system that we fielded, and Mayhem is fielded on a lot of academic research based upon binary analysis. Binary analysis is just a fancy term that says we analyze off-the-shelf software as you're delivered. And the reason this is so important is what this allows us to do is find vulnerabilities without developer cooperation. Right now, we're living in this weird world where developers write software, they have a whole bunch of security tools that can tell you whether or not it's vulnerable, but they don't tell you the results. However, when you install that software, you're the one who pays the penalty, not the developer. So we've been looking at this, and we developed this suite of technology so that we could finally empower end users to check the software that they run. When we take that software, the first thing that we do is we harden it. So we apply common security mechanisms, essentially seatbelts, to the program that protect against common attacks. We then look for exploits. We go through the binaries and we say, hey, can we find those exploits like I just showed you? And if so, we patch them. Once we come up with an autonomous patch, we have to test it and make sure that that patch doesn't break anything and make a decision on what to deploy. Now, for those of you paying careful attention, you'll notice I talked a lot about defenses, and I put out a couple terms. First, we have the original unprotected program. You can harden it. Once you find a vulnerability, you can patch it. Maybe you can do patching plus hardening. At the end of the day, we had 4 different choices in the Cyber Grand Challenge. We could go forward and decide that at this state in the game, we just want to play the unsecure binary. For example, we don't have a security solution that we think is effective or performant. We could play the most expensive solution if it seemed appropriate at the time. So we had to have a strategy for doing this. Finally, we would deploy it and then go back to square one. We'd observe the state, try to decide what our attackers are doing, try to decide what's best for us, and start all over again. So to give you an idea what patching looks like, this is uploading the SQL Slammer worm that plagued the internet some years ago. It was prepared by DARPA specifically for this contest, unbeknownst to the contestants. So our system first automatically starts generating test cases for it. And the reason that we do that is when we find an exploitable bug, we have to patch it, and we have to make sure we didn't break anything. No one wants to install software that breaks things. We then measure the effect over the whole system of our approaches for patching and hardening. That's what we called scoring. So here we're replaying the test cases against a hardened binary. You'll shortly see one played against a patch specific, and we'll make a decision. Now in this case, when we patched the problem, when we hardened the binary, they had no performance loss, they had no functionality loss, so we would play the best security solution. But it wasn't always the case. Sometimes we would come up with binaries where we had no effective security solution. We just continue with the undefended binary. So that was the overall game. The overall game was one of attack and defense. It was one about evolution. And it was one about protecting the software that you're delivered at machine timescales, not human timescales. DARPA put up a $2 million cash prize for the winner, which was nice. But they also hosted this at DEF CON, the world's largest hacking contest, where in front of 30,000 of our peers, our system, our decade of research was tested against others in the field. And I think one of the things that you'll see here is in the final round, after all is said and done, DARPA had selected 7 finalists, many of them from academia. University of Idaho, Berkeley, UCSB, and our spinoff from Carnegie Mellon for All Secure. General Nakasone talked about the importance of involving academia. I think you'll notice that only one government contractor is appearing on this slide. So reaching out to those non-traditional performers and allowing an open playing field determined purely by technical merit, as opposed to whether you know DCA compliance rules, I think was a big win. So this contest went over the entire day. It was the most nerve-wracking time of my life. I was sitting there eating red vines all day, not eating real food, because our systems were playing and we couldn't do anything. At one point in this contest, we had a hard drive failure. And you know what? We couldn't walk up to these machines and just replace our hard drive. At one point, our system stopped responding, and we weren't sure why, and we couldn't debug it. We had no access because it was a completely autonomous system. Turned out, after analysis, there was a denial of service attack that was slowing down our system, and so we weren't able to respond within the times. So the competitors are all sitting there very, very nervous, and I'm happy to say that at the end of the day, we won. So I was really excited to get this $2 million, which we split among our team members. But it was also really cool talking to the other contestants and talking about the shared technology, the little tips and tricks that we all brought to it, and everyone's passion for making computer security autonomous, for taking the human out of the loop. So this was the final scoreboard, and one of the things I hope you'll appreciate from this is that there was a lot of competitive tech. When DARPA ran the very first grand challenge on autonomous driving, the cars fell flat. They didn't go anywhere. When the Cyber Grand Challenge ran, we had 7 finalists who all competed at a world-class level. You'll also see that team size didn't necessarily mean the most effective. For example, the University of Idaho, GEMA, second from last year, was extremely competitive, but they only had 2 people who built the entire system. Pretty amazing, huh? I also had the pleasure of witnessing our tech then go on to play the world's best hackers. I started off by showing you a picture of Loki. Loki, who can find new zero-day vulnerabilities in a weekend that breaks into 85% of the world's web browsers. He plays for a team at DEF CON called DEFCOR. Now, our system entered this hacking contest to go against the best humans, and it lost. But one of the things I'm proud of, and I think if you look at this, it was competitive. DEF CON went over 3 days, and for the first 2 days, Mayhem was beating the last 2 teams, Samurai and OneSpam and Hex. I won't say who the members are, but in the hacking world, we also often use these funny nicknames to really hide who we really are, because we all have daytime jobs. So Mayhem was competitive with it. Now, I also, at Carnegie Mellon, am the faculty mentor and founder for PPP, the CMU hacking team, which has won DEF CON 3 out of the past 4 years. So I had this really interesting insight into what the best competitors were doing and what the autonomous system was doing. And I can tell you, the system was finding new exploits at DEF CON that PPP missed. PPP, this top hacking team, saw the code, saw the exact same code the system did, and missed it. I also saw the machine respond faster on defense than most of the teams did for turning around new patches. Now, I can tell you where these best hackers excel. It's really in creativity. In a DEF CON contest, these are the world's hardest problems. I mean, imagine a kid, 21-year-old kid who can find 0 days in Chrome, a big software package. For him to be playing at DEF CON means these problems have to be hard to keep his interest over 3 days. And what these top hackers are able to do is they're able to use their creativity and intelligence to break down large problems, find unique solutions, to come up with new ways of attacking problems that the computer wasn't programmed to do. So I think there's always going to be a place for humans. I don't think autonomous systems are going to replace humans. I think what they're going to do is they're going to augment them. They're going to allow the human to be free and explore these creative pursuits. To give you an example of one of these creative attacks that the machine can't find, it's something called a timing attack. So if my wife asks me, do I look fat in these pants? And I take any amount of time to respond, I've kind of revealed the answer. It's the same thing in crypto. When you ask a server to decrypt something, the amount of time it takes to decrypt can leak the secret. Not something the computer was programmed to do, but something that was in some of the DEF CON problems that these humans were able to come up for attacks against. So I've been thinking about the road ahead and what the Cyber Grand Challenge meant and what I think the US should do. And I think the first thing is we need to start increasing the scope that we can apply these systems. When DARPA created the Cyber Grand Challenge, they kept it in an artificial playground to level the playing field. We proved the technology is possible, and now it's our time to adopt it to real life. And part of the challenge, especially as we look at some of the more critical vulnerabilities in things like weapons platforms, we have to make it analog aware. Well, I like to think the entire world is digital and it's powered off my iPhones. When we look at reactors, when we look at planes, ships, and trains, these interact with the real world. They're cyber-physical systems, not just in the digital domain, but in the analog domain. So we have to consider that. And one of the things that I'm really excited about, especially in the Army, is they embrace this idea of the analog plus the digital, and they embrace it publicly. It's not actually a very common thing to do. After we increase the applicability, I think we need to start looking at automatic analysis. We need to start talking about, can we analyze 13,000 programs, 37,000 programs, find 13,000 bugs for 29 cents a piece? When we get to that point, we're going to have the sort of scalability that other countries don't. At that point, we can also start ceding decision control because we'll have enough data to decide, is it making good decisions consistently? I tell you, when you look at AI, one of the worst things you can do is go look at a small data set. And the reason for that is you're going to get a lot of bias. And in the real world, things are messy. You need a lot of data in order for AI to make a decision. At the same time, though, I think we also need to start thinking about counter-autonomy. Now, in the Cyber Grand Challenge, they left out counter-autonomy. And what I mean by that is something that takes that autonomous system and goes after it. Because in some ways, once you create the self-driving car of the future, If you can find a flaw in that one self-driving car, you can cause traffic accidents everywhere. You're putting all your eggs in one basket. Same for cyber autonomy. And although it wasn't part of the competition, we started to investigate this. For example, we found 0 days in other people's tool sets. For example, Raytheon was rumored to be using a very well-known tool set using the hacking community called IDA Pro. And we found new vulnerabilities in IDA Pro. And we were able to rewrite our binaries so they would run as normal, but if you happen to analyze them in IDA Pro, we could shut off your computer. Now, it was outside the scope, but it just goes to prove that we could create things that ran as normal but would attack the autonomous system. And until we start thinking about these things together, we won't really know how much control to cede. Because until you start reasoning through, when I cede this control, this is how reliable the system will be, you won't really be able to make an effective decision. So when we look at like self-driving cars, I think it's good, but I think we also, especially in cases like that, have to start thinking through the cyber implications because of the large-scale effect if we make the decision point wrong. I'm also happy to say that the DoD has started to move forward with transitioning these technologies into practice. And a large part of that has been about innovation and about thinking outside the box. In fact, the DoD set up an organization called DIUX, and their entire goal was to make it so small companies with innovative solutions didn't have to think about this thing called DCAA compliance, to make it easy to get on contract, to get it fast on contract. And they created a project called Voltron, which is really a collaboration across the DoD to take the cyberground challenge tech and start moving it forward. I think it's a great effort. I think it's something where people can participate. If you have funding, it's something you put funding towards. But I also kind of want to give you a sense of scale here. When you build a new major weapons platform, we're talking about hundreds of millions of dollars, maybe billions of dollars that go into R&D for that system. When we're talking about developing the tools that will protect those systems from cyber vulnerabilities, we're talking on the order of millions today. Fractions, 1% of the price. And I think that we can do it for a fraction of the price, but I think it might be a little bit more than that. I think it's something that we need to continue investing in. I think it's also important to realize that DARPA ran the Cyber Grand Challenge and put it on a world stage in front of the world's best hackers, and that also sent a signal to all our adversaries that this tech is real, and they're doing investment as well. And if you think about it, this tech can benefit the US, but if we fail to adopt it, it can also benefit those much smaller countries and start giving them an asymmetric advantage. So with that, this talk really only had two themes. The first one is human effort doesn't scale. We can go get the world's best hacker and he can have a profound effect in a particular engagement, but at some point in time, it's just gonna be a person-on-person battle. Do they have more people than us that can do it? And we already know world population, it's very easy to do the arithmetic, it just doesn't scale. And so we have to look to technology, and we can teach computers to hack. That's all I have. Thank you. Questions? I'm happy to take questions.
We have time for a couple more questions. One?
Hi, thank you so much for the presentation. It's very interesting. So my question is just around when you start talking about teaching computers to hack, the data used to train AI or autonomous technology, if that data has bias in it, as well as those actually developing it has bias in it, how do we ensure that some of the human limitations of bias as we start moving towards AI and autonomous systems don't also end up within the technology and then don't have the human balance of empathy or the creativity that you speak to?
That's a great question. So I want to address it in two parts. First is to some of the technical aspects of what we saw in the CGC and the tech base there, as well as more general. So in the Cyber Grand Challenge, it was billed as an autonomous cybersecurity competition. And autonomy requires some amount of AI, but we did not use a huge machine learning or data science stack. In fact, NVIDIA called us up and offered us some of their latest GPUs, and we had no use for them. And so I think this idea of the data sets having a skewed offset is something that would affect some domains, but not necessarily software analysis. Mostly what we built, the technology for finding, for example, exploitable bugs, is hardcore formal analysis. Now, I do think that human bias does have a profound effect somewhere else, which is where we code these computer systems to only look for certain types of attacks or take explore certain ways to go about things. It's also in when humans start hard coding in rules the rules of warfare, if you will, about how you should go about things. When we had our cyber reasoning system, we had a pretty advanced strategy. For example, if you exploit me, one of the cool things about the digital domain is now I get that exploit for free. It doesn't hold in weapons, right? Weapons explode and they're not reusable. But cyber weapons are, and I can use it against other people. And being able to use AI to start reasoning through these different scenarios, I think, is one of the places that we have to be careful not to be too indoctrinated in what we see today so we can explore the full spectrum and not get hit by surprise.
Yes. Hello.
Yes.
Dr. Brumley, first of all, thank you for the talk. Very interesting stuff. Cool work. Appreciate it. You're going to put me out of a job. My question to you, because ultimately Cyber Institute is about training, you talked about the difference, you talked about creativity.
Yeah.
And what I'm asking is the difference between the structured and the unstructured. Ultimately, Cyber Institute is about teaching that creativity in a structured environment. Do you have any insights on that?
Yeah. Well, I have opinions, not insights. So at Carnegie Mellon, I've run this hacking team, PPP, which has been one of the #1 ranked teams in the world for many years. They win a lot of DEF CON. So I can tell you how we go about training and how we go about creativity. And I tell you, there's no substitute for understanding the fundamentals. You can't start focusing on creativity before people even know how to do a basic exploit. And the way we go about it is much like you would do any other education, where you go and you break problems down into their smallest components. You teach people how to solve those, and then you give them a little bit harder problem. You give them a little bit harder problem. And what you find, if you keep doing this over time, they get better and better, but they start getting a feel for things, and that's when creativity sets in. And I don't think this is so different from a musical instrument. You don't hear about people being creative virtuosos on a guitar or piano before they're able to be reasonably good in the basic instrument. And so to me, I think it's kind of a two-pronged approach. First, you have to give people those basic skills, and you really have to focus on, do they know the fundamentals? And then you have to give them the freedom to go use them. So how do you give them the freedom? I'm a big believer in hacking contests. Hacking contests are only about creativity. The way a hacking contest works is if we break into a system and we steal a file, we get points. We do not get measured on how we went about breaking in that system, whether we went after the expected vulnerability or not. For example, I went into a hacking contest once where the way you were supposed to break into the system, the way they had set it up, is there was a vulnerable web server running a vulnerable web script. And a Dutch team found a brand new zero-day vulnerability in PHP, the application interpreter, the same thing used by Yahoo, and broke into that. They found a different way into the system. And so I think you find these, what you do is you teach the basic skills, and then you put them in these simulated full spectrum combats. We don't measure how they got to the top of the hill. You just measure them whether they did get to the top of the hill. Thank you. Yes.
Good morning, Dr. Very interesting presentation. Colonel Forrest Hare from Department of Defense, obviously, the losing football team. I guess we'll go ahead and point that out. About 10 years ago, the Air Force Cyberspace Task Force was sitting over at Carnegie Mellon SEI, and we're getting a presentation from the staff. And one of the things that they presented, which I was not aware of, I'm a targeteer background, I'm not a technologist, but I've been in the field for a while now, is that unlike the fields of aeronautical engineering or building buildings or something like that, where we can do a lot of computer modeling to see how it's going to function and how we can adapt it before we field it. Ironically, computer science and building programs and stuff, we seem to be much further behind. You know, we can build a program and compile it, make sure it runs, but how it's going to actually function in the field is we seem to be much more behind compared to all these other fields. Do you see what you're doing here as helping us to, first of all, you can maybe correct me if I didn't quite characterize that correctly, but assuming that's the case, do you see this, what you're developing here, helping us take some significant progress to address that, and to the point where we can start fielding, we can look at these programs before we even field them and make sure that they're more secure and functioning more properly, so that we don't even have to go in the wild? Or do you still feel you still have to go out there and test it in the wild a lot more, if that makes sense?
I think that's a good question. So to be fair to computer science, we're a really new discipline compared to buildings, right? We've been building buildings since the Stone Ages. And so computer science, we don't have that sort of history and experience quite yet. And we're learning as we go. I think when you look at things like the Cyber Grand Challenge, what you get into is you get to systematize testing. For example, I feel more comfortable fielding an automatically generated patch than one that than my students or my team created. And the reason for that is my computer system has a system for testing everything that's well documented, well understood, and is testing millions of different variations. And so I think one of the roles of autonomy is bringing that sort of systematization to the field to make sure that what we're building, where we allow the humans to be creative, we can allow the computer to help test that. I don't think we're there yet, but I think that this is a big positive step in the right direction.
I think that's all that we have for questions. Would like to thank Dr. Brumley for coming out today, for his leadership.
Oh, thank you.